Okay, well, in today's session, we will look at single source shortest path problem. Now, this problem is also part of the greedy method. Now, to solve this problem, single source shortest path problem, we use something known as Dijkstras algorithm. And actually, Dijkstras is the one who has designed the solution for this problem. So it's called as Dijkstras algorithm. Now, this single source shortest path problem, though we are looking at solving this problem using greedy method, that is one of the problem solving technique. We will also look at how to solve this problem using other approaches, other strategies. That is the next part which we are going to take up is the dynamic programming. So both the ways this problem can be solved. It can be solved using greedy approach or greedy method as well as using dynamic programming. So in this session, we will look at how to solve this problem using greedy approach or greedy method. Now, before we move further, let us look at what this problem is about. Now, till now, what we have seen is a problem which consists of weights, and you try to fill the sack according to that constraint. Or we have seen something known as we have some deadlines and the jobs has to be done according to those deadlines. We have seen other sorting problems using the divide and conquer approach. Now this is a completely different set of a problem, kind of a problem. Now here what we have is we are given a set of vertices. Now these vertices in general or real time generally are nothing but they are cities if you consider set of vertices, and these vertices are connected. So suppose if we consider this set of vertices and we have paths, these not all vertices will be connected with another vertex. There might not be any possibility there that all vertices should be connected to the other vertex. For example, if you see New York is not directly connected to Los Angeles, but in a graph, this is actually a graph. In a graph, vertices will somehow be connected with direct path or indirect path. And the connection is nothing but using edges. So any two vertices can be connected through an edge. And these edges may represent different types of values or different types of what we say is, for example, in this case, it's a flight plan. It's a flight plan there, a flight path. Or you may have a car, maybe a road network. So you can drive through those road network. So the weights are assigned to edges. Now these weights may represent the flight time, or it may represent the cost of the ticket, or it may represent other different criteria can be used to represent these cost or weights of the edges. So this is basically a graph, and what we have is single source shortest path problem is a graph problem. So now when we move further, what we need to solve is we need to find single source shortest path. What it means is we need to find from some vertex what is the shortest path to reach other vertices. Now this problem we solve it so that we can directly say that, for example, in this case, what is the travel time, or when we are traveling from New York to Los Angeles, there may be several questions that we will be able to solve. That what is the shortest, fastest way to travel from New York to Los Angeles? Or which route will be least expensive when the weights are considered as airfares? Or we may also solve the problem of shortest distance when we consider the set of the edges with the weights as nothing but representing the distance in kilometers or miles or so and so. So the questions can be answered using single source shortest path. Now, as the name suggests, single source, any vertex can be taken as a source. And from that vertex to all the other vertices, we need to find the shortest path. So now let us move further. This is another example of travel time what we take moving from driving. Earlier example was an airfare. This example is nothing but instead of traveling by air, if you want to drive, then the same questions can be answered using the single shortest path solution. Now let us consider this as an example graph. Set of vertices, you can know that they are cities, and set of edges is nothing but road network. And or set of vertices can be your routers, network switches, and the set of when we consider vertices as routers or switches, the set of edges can be nothing but a communication line connecting two different vertices or two different switches. So a graph is generally represented using G, a set of vertices V as a set with vertices V and edges. Now if we consider this V is nothing but again itself is a set of vertices. So we have 6 vertices here and we have edges. Now all these are, the arrow represent a directed edge. Remember that there is an orientation here, so this is a directed graph. Now let us consider source vertex V. Now suppose if we are considering vertex 1 as V. Now remember that single source shortest path problem. From any vertex you can find shortest path. You can choose any vertex. It can be 5, it can be 3 or any vertex. But usually what happens is when the problem is asked or when we try to solve a problem, we consider the first vertex as the single source vertex. That is the start vertex. But remember you can consider any vertex. So let us consider one as the vertex 1 as the source vertex. Now let us solve the problem of determining the shortest path from vertex V, that is the source vertex, to all other vertices. That is the single source shortest path problem that we are trying to solve. Now before we move further, let us look at something known as a path. Now when we say shortest path from source vertex to all other vertex, let us consider single vertex. Shortest path from vertex 1 to vertex 2. Now they can be a direct path or they can be a sequence of edges through which we reach the destination vertex. So path is basically from any vertex V to any vertex V, which is a sequence of one or more edges. If it is one edge, it's a direct path we call. More edges, we call it as a path which may have an intermediate node. Now let us consider same vertex 1 as the source vertex V and vertex 2 as some vertex U. Let's say this is the destination vertex U, vertex 2. Now path from vertex 1 to vertex 2, we have path A. There is a direct path whose cost is 50. And then we have another path B through vertex 1 to vertex 4, from vertex 4 to vertex 5, and vertex 5 to vertex 2. So there are two paths. There may be other paths also. For example, from vertex 1 to vertex 3 to vertex 5, then vertex 5 to vertex 2. But let us consider these two paths. Now the cost of the path A to reach same source and same destination is 50 because there is a direct edge here. The path B is the sum of the edges, that is sum of weights of the edges on that path, or sum of cost. So 10 plus, we have from 4 to 5, 15, then from 5 to 2, it's 20. So this length is 45. Now there is a direct path and there is a path which flows through certain intermediate nodes or intermediate vertices. So But don't think that a direct path will always lead you to a shortest path. That may not be the case. The direct path, sometimes indirect path may also lead, though you have to, travel through several intermediate vertices, but path with sequence of vertices may also be used, which may be a shortest path. So in this case, path B is shortest. Now this way we have to find shortest path to all the other vertices. So let us look at another example. Let us consider vertex, before we move further, let us look at another example. Let us consider vertex V as 1 and vertex U as 6. Now what will be the path from vertex 1 to vertex 6? Is there a direct path? No. Is there an indirect path, in the sense a path traveling through several different vertices? That is also not possible, because this is a directed graph and vertex 6 doesn't have any incoming edge. So there is no way that we can reach, whether through directly or through any other path. There is no way we can reach from vertex 1 to vertex 6. In this case, what we say is the cost of the path is infinity. We say is, since we cannot reach from vertex 1 to vertex 6, we say the cost of the path is infinity. So this was the very basics of what path is and how we solve the problem or compute. Now, let us come back to the Dijkstras algorithm or single source shortest path problem. The same thing, determining shortest path from source node V to all other vertices. Now here, the criteria or the optimization part is nothing but the cost should be minimum. That is, the length of the path, whatever we generate, has to be minimum. It's not maximization problem. It is minimization problem. So the optimization criteria here is minimum. It's based on the what the cost we get as minimum. So remember, knapsack problem, the optimization criteria was maximization. It was a maximization problem. Criteria there we use is maximum of the profit. Job sequencing deadline also, it was a maximization problem. What we use the criteria there is to maximize the profit, what we achieve in completing the jobs using within their deadlines. But this problem is a minimization problem. So the optimization is based on the cost or the length of the paths generated to be minimum. Then how do we solve this? Because we have to find from different till different vertices the shortest path to all other vertices. So how do we solve this? We use something known as Dijkstras algorithm. The basic concept of the Dijkstras algorithm, the working of this Dijkstras algorithm, it is based on the assumption that all weights are positive. If the edge has a negative weight, then we will not be able to use, or Dijkstras algorithm will not give us the correct results. Sometimes it gives us the correct result, but not always. So Dijkstras algorithm assumes that all costs or all weights of all the edges are non-negative, they are positive. If it is negative, Dijkstras algorithm doesn't work. Then the path, the sequence of path, how we discover. That is because we need the total cost. Is we look at in the order of their weights. So we discover one path, its cost will be something. We discover another path, and if its cost is less than the cost of the previous path, then we update the path, the cost there. That is how we try to discover according to their weight. Then This discovering path according to that weight, because there may be several paths, is basically based on something known as relaxation technique. And this technique is based on the minimization or minimizing the length of the path. Now let us look at what the minimization, the relaxation technique is to minimize the cost of the, to find the minimum cost path. Now here, there is a equation which we need to solve, or there is actually a condition what we need to solve. That condition of the relaxation technique is if the distance of any vertex W is greater than the distance of vertex U plus cost of vertex U and vertex W. So what this means is, if this is true, if the distance is greater than some distance of cost U plus cost of U to W, then update the cost, update the distance using the cost. So it's nothing but whatever cost you found now, which is supposed to be less, because when we say distance of W is greater than this, obviously that means this part is less. So assign the lesser cost, the value to the distance. That is nothing but you update the distance. Now let us look at how this works. Now let us consider vertex 1 as V. Now equation doesn't have something V, remember, so don't get confused. This is the source vertex. U is the destination vertex. Now in this case we are considering 4, just as an example. We are considering 4, vertex 4. Now the distance of 4, so U is vertex 4, so distance of 4 is nothing but from vertex 1 to vertex 4, that is 10. That directly is the cost, direct edge, the cost. So distance of 4 from 1, because 1 is the source vertex, is 10. Then let us consider vertex 5 as W. Now initially, is there a path from vertex 1 to vertex 5? Direct path? No. So therefore distance of 5, that is distance of W, here we have W here, distance of 5, distance of W 5, means distance from source vertex, that is vertex V. This distance, there is no direct path, it will be infinity. As we have seen in the previous example, the cost from of the path from 1 to 6, we cannot reach 6, so it's infinity. The same way, at this stage, we cannot reach from vertex 1 to vertex 5 directly remember. So it is infinity. Now let us put this thing into this equation. So what is cost of W? Cost of W is infinity. Infinity is greater than distance of U. What is U? U is 4. Can we reach from vertex U to vertex 5? That is vertex 4 to vertex 5? Yes, we can reach. So distance of vertex U is 4. This is 10. So 10 plus cost of U to W. So what is this distance of 4? It's 10, means from 1 to 4. So it's 10 plus reaching 5 is this cost of the edge from 4 to 5. So cost is nothing but this cost of U comma W is the cost of the edge. Is the cost of the edge, that is 15. So if we have 10 plus 15, which will be 25. So 25 over here, I have simplified it. 25 will be, this is infinity, distance of 5, currently infinity, is greater than 25? Yes, it's true. So what do? you update the distance from 4, u, distance of u plus cost of 4 comma 5. So now distance of 5 will become 10 plus 15, which is 25. So instead of infinity, this will change to 25. So whenever we find relaxation technique, whenever we find some distance from vertex u to some vertex w less than the previous distance, we update the distance. Now before we move further, let us try to take another example. What is the distance of vertex 2? Distance of vertex 2 means always the cost of the path from the source vertex, that is vertex v. So distance of vertex 2 is nothing but from vertex 1 to vertex 2, what is its distance? We have a direct edge, so it is 50. So distance of vertex 2 is 50. Now, do we have any other path to reach vertex 2? Yes, we have from 5. From vertex 5, we can reach vertex 2. And vertex 5's distance, we already know it's 25. We computed. So now, let us consider W as vertex 2. That is, we are trying to relax or perform relaxation technique on vertex W, which is vertex 2. So distance of vertex 2, currently it's 50, is greater than distance of 5. Distance of 5 is 25 plus cost from 5 to 2. 5 to 2 is 20. So 50 greater than 25 plus 20 is 45. So obviously 50 is greater than it's true. So distance of, sorry, this should have been 2 over here. So distance of 2 will be updated to 45. So here there is a mistake in the slide. Distance of 5, I have it over here. It should be distance of 2. Distance of 2 will be 25 plus 20, which is 45. So we found a path which gave us the less distance. So we updated the distance. That is what is known as relaxation technique. That is, we try to relax the path here. So if we find a path which is less cost or which has the less distance, then we try to update it. Else we don't update it. If you don't find a path, or if you find a path which has the distance more, then there is no need to update. So what this means is, to reach vertex 4 from 1, always from 1, the distance is 10. To reach vertex 5, distance is 25. And to reach vertex 2 from vertex 1, distance was 50. It got updated. Now to reach this vertex 2, the distance is 45. So this is how relaxation technique works. Now, the Dijkstras algorithm starts by considering all, obviously, whatever we have seen, this thing is just an example of a particular vertex 4 or vertex 5 or vertex 2. So we have to look at all the other paths to reach all the other vertices from vertex 1. So this is not just, we cannot do it ad hocly by randomly taking every vertex and trying to find what is the different. There has to be some sequence of steps that is involved. That is known as the algorithm there, known as Dijkstras algorithm. So let us try to solve this problem. Now this is a directed graph with 6 vertices, and we have a cost, each edge assigned a cost. Now we say cost or weight, which is similar, but remember that if a vertex is, if there is no edge, direct edge between two vertices, then it is infinite. The cost is infinite. That is, we say that directly we cannot reach that vertex. But suppose if there is an edge between two vertices, direct edge, then it has some cost or a weight. Now if there is an, if the vertices are same, then we assign 0 as the weight because we will not be considering self loops for graphs in this solution for this Dijkstras algorithm. Now this graph is represented using cost adjacency matrix. And in the cost adjacency matrix, row will be representing vertex as well as column will also be representing vertex. So every time when we say I comma j or a value from I comma j, I means the vertex, start vertex, and j means the end vertex. So the weights are assigned using I comma in the ith and the jth, ith row and jth column. Diagonals are 0, and if I is not equal to j and I and j is not an edge, then everything is assigned as infinity. So if there is no direct edge, then it is infinite. Now, since we are solving a single source shortest path problem, what we have to do is, here we need to consider, just a second, my recording is on. Okay, yeah, sure. Recording is on, doesn't matter. Anyway, now since we are trying to solve a single source shortest problem, we consider the first vertex as the start vertex and we represent that with u. Then we will try to find what is the shortest path to all the other vertices. Now remember that in the last session we have talked something about relaxation technique, and that relaxation technique or relaxation rule we will be applying and solving this problem. Now let us start by taking vertex 1 as the start vertex. Now usually vertex 1 is taken as the start vertex, and from there we try to solve, and we call this as vertex B. Now on the top, if you see on the slide, we have the relaxation rule or relaxation technique. Anyway, we'll look at this, how this relaxation technique is applied. Now we will be maintaining an array S, known as S, and this array is a Boolean array. It will be storing true or false or 0 or 1. The length of this array S is the number of vertices. So we have total 6 vertices, so the length of the array will be 6. Now remember, in programming, when we use programming language, the array starts with index 0, but this is the algorithms, and we have talked in the various other classes that for the in algorithms, we usually consider the start of the start index of an array with 1. So we have 6 indices, and each index represents a vertex, and S is a Boolean array. Then we will maintain another array known as distance, DIST, which stands for distance. Now remember, this S is only an array and single array with this indices, but distance, it's looking like a matrix. Now this is not actually a matrix, it's an array. Why we have taken, or why I'm representing this dist array as a matrix, because I want to show you what is the previous value and how values gets updated. But anyway, at a single instance, this is going to be a one-dimensional array, and the length of this array is also 6 because we have 6 vertices. Now the very first thing is, this dist array is, as the S array is initialized, all the vertices are initialized as false. So you can see true over here, but all are initialized as false initially. And then what we have is, we have the initialization of the dist array, and this dist array will be initialized with the cost of the edges. Now dist of 1, means distance of 1. From where? From 1 itself, because start vertex is 1. Vertex V is 1. So dist of 1, distance of 1 from 1 is always going to be 0. So this column, dist of 1 column, we're going to have 0 for as the values. Then what is the distance of 2, vertex 2? Distance of vertex 2, there is a direct edge with cost as 50. So we will have 50 over here in dist of 2. Then in the same way, dist of 3 will be, there is a direct edge from vertex 1 to vertex 3. So distance of 3 is initially 45. Then distance of 4, that is vertex 4, is, we have a direct edge with 10 as the weight, it's 10. Then what about 5? Distance of 5 from vertex 1. There is no direct edge. So initially, it's going to be infinity. As well as vertex 6. There is no direct edge. So initially, it's going to be infinity. Then once we have initialized the dist array and array S, what we do is we will make the first vertex in S as true. That is why I have true over here. Initially it will be false. So first, if you observe here in array S, the first vertex will have, or index 1 will have true. Then we have already initialized the distance array. Then from the distance array, we will choose the minimum distance and then work with it. Now what is the minimum distance? What is the minimum distance? Here we have minimum distance as 10. This 10 distance belongs to which vertex? It's the distance of 4th vertex or vertex 4. So we will consider vertex 4 as vertex U. And in S array S, we will make this. So over here, even over here, the value of 4 in array S will be false. We will make this value as true. Now, vertex 4 is having out degree 2. That is, there are 2 edges which are going out of vertex 4. One edge is going to vertex 1. Now obviously we don't calculate the distance of vertex 1 from vertex 1, which is it's going to be 0 always. So this is not considered. Then there is another edge going from vertex 4 to vertex 5. That is, which has a value as 15. That is, the cost of the edge is 15. So now remember that we are choosing vertex 4. Remember, why are we choosing vertex 4? We are choosing vertex 4 because vertex 4 had the least distance. Vertex 2, obviously we don't consider vertex 1 because it has 0 distance apart from vertex 1, apart from start vertex. Vertex 2 has 50 distance, vertex 3 has distance 45, vertex 4 has distance 10. So 10, this is the least distance, that is why we are choosing vertex 4. It's not that you can choose any vertex. The algorithm selects the vertex which has least distance. So that is why we are selecting distance 4. And from 4 to 1, we have an edge, but we don't calculate distance for 1. So we don't consider this. And we have another 4 to 5. Now, remember, this edge from vertex U to the other vertex is known as W. So we have vertex W is pointing to vertex 5. Now let us apply the relaxation technique. So relaxation technique says that distance of W is vertex 5, is greater than, if it is greater than distance of U, which is distance of 4, vertex 4 plus cost of U comma V, that is cost of the edge from vertex 4 to vertex 5. So then if this is true, then distance is updated. Distance of 5 is updated. So here what we have, distance of 5 is infinity. Greater than distance of 4, which is 10, plus the cost from 4 to 5 is 15. So infinity greater than 10 plus 15 is 25. which is true. So what happens is, instead of the value infinity in the distance array for vertex 5, we update that to 25. We change it, we update it. That is what is the relaxation rule. We change it. So instead of infinity, we update it to 25. Now, what about the rest? Rest of all the other distance values remains the same. Then, in the next stage, what do? We have to choose the least vertex which has least distance. It is 10. Now 10 is for vertex 4. Then we will look in the array S whether vertex 4 has already been visited or not. We have true, so vertex 4 is visited. So we consider the next least distance, that is, it will be 25. 25 is for vertex 5. So now vertex U becomes vertex 5, and we change this to true in the array S. That means we are computing now for vertex 5. And then from vertex 5, we have an edge to vertex 2 as well as vertex 3. So we will consider vertex 2 first. So vertex 2, we have distance is 50. So let us try to apply the relaxation technique. In this case, we will have distance of W is 2 in the first case. So this node 2 greater than distance of 5, that is U, which is vertex U plus cost of 5 to U. So distance of 2 is 50 greater than distance of 5 is 25 plus distance of the edge plus the edge, cost of the edge from 5 to 2 is 20. So 50 greater than 45 is true. So we update the distance of vertex 2, and now vertex 2 will have the distance as 45 instead of 50. What about the rest of the edges? We again have to compute because we did till 2. Vertex 5 also has an edge with vertex 3. So we will compute. Now we will consider W as vertex 3 and compute the distance. So I'm having it here, distance of 3 greater than distance of 5 plus cost of 5 comma 3. Now this is 45, distance of 3 is 45, and greater than distance of 5 is 25 plus cost of 5 comma 3 is 35. So 45 greater than 25 plus 35 is false. So we will not update it, and rest of the other values remain the same. So we are done with vertex 5 also. Now let us consider the next case. We will choose what the least cost, which is 10. In the S array, it is true. So we have visited this vertex 4. Then the next is 25, which is also true. So we find the next least. We have two vertices here, vertex 2 and vertex 3, both are having 45. But since we have to solve it programmatically, so 2 comes before 3, so that's why let's select 2 as vertex U. Now vertex 2 has 2 edges going out, that is from vertex 2. Obviously, we make the vertex 2 in array S as true, and then we have 2 vertices. So the first first 2 edges from vertex 2, that is first edges from vertex 2 to vertex 3 with the cost 10. So let us consider 3 as the vertex W, and we will perform the relaxation technique. So we have distance of 3 greater than distance of 2 plus cost of 2 comma 3. So distance of 3 is 45, which is greater than distance of 2 is 45 plus cost of 2 to 3 is 10, which is false. So we don't update. We will consider vertex 4 because we have an edge from vertex 2 to vertex 4. So we already did 3, we consider vertex 4. Now in this vertex 4 is already, we have already examined this vertex 4. So there is no need to update because we have S, we have true in array S. Then let us perform the second round, the next round. In the next round, and again 10 is selected, which is already done. 25 is the next least, which is also done. We have 45 for vertex 2, which is also true, done. So we have now 45 for vertex 3, which is still false. So we need to now compute vertex 3. Now vertex 3, we will make it as true, and vertex 3 is considered as vertex U, and then the vertex W will be vertex 3 only has an edge to vertex 5. And this vertex 5, here we perform the relaxation technique. What we say is distance 5 is 25 greater than distance of 3 is 45 plus cost of 3 to 5 is 30. Actually, it's not 35, it should be 30. There's a mistake here. So, which is false. So it doesn't get updated. Now remember, last time when we had from 2 to 3, from vertex U we consider as 2, we had 2 to 3. There was an edge, we computed that. Then we also had 2 to 4. But we did not compute 2 to 4. I said that it's already done, so there is no need to update that. Even in case of 5, it is actually done already because 5 is true here, so we don't need to update anything. But the thing is, what I wanted to show here is, even if we consider vertex 5, that is the edge coming from vertex 3 to vertex 5, will not be able to, there will not be any way of updating. It doesn't get updated. So that is why you can even if you perform the relaxation rule, it will not get updated. So instead of performing the relaxation rule, we can directly look at the array S, where we have the vertex W. If it is false, then we'll try to apply the relaxation rule. If it is true, we will not apply the relaxation rule. So that way, we will be able to save the computation time. Then obviously this is done. The last instance what we have is vertex 6, which is only left out vertex. All the other vertices are true. Now this vertex 6, if we consider as vertex U, there will not be any other there is no way that we will be able to update other distances of other vertices, because from vertex 6 we can only go to vertex 5, and there is no incoming edge to vertex 6. So vertex 6 remains the same, and the distance of vertex 6 will not get updated, and it will be infinity, because there is no way that we will be able to reach vertex 6 from vertex 1. And what we have at the end when this algorithm completes is I have darkened the previous values, and what we have is the final value as 0, 45, 45, 10 and 25, and finally for vertex 6 infinity. So actually this is the actual array and the final values what we have. So what we say here is, we say that from vertex 1 to vertex 1 its distance is 0. From vertex 1 to vertex 2, single source shortest distance is 45. From vertex 1 to vertex 3, it's 45. From vertex 1 to vertex 4, it is 10. And from vertex 1 to vertex 5, it is 25. And to vertex 6, it is infinity. So this is how we apply the Dijkstras algorithm to compute the single source shortest path. And finally we have this result. So this is how Dijkstras algorithm works. Now let us look at the actual algorithm itself. Now this algorithm in the textbook, though some places it is called the Dijkstras itself, and some places, I mean, in your prescribed textbook, it is called as the shortest path algorithm, but this is nothing but the Dijkstras algorithm itself. And next the thing is, and the next thing is, and this algorithm, shortest path or Dijkstras algorithm, takes V as the set of vertices, cost as the cost adjacency matrix, distance, the array, where initially, I mean, this is the array which is passed as parameter, but once the algorithm completes its execution, the distance array is going to have the final distances of the shortest paths, and n is the number of vertices. The first thing is the initialization part. So as I said, we have an array S. This array S is initialized to false. All the indices is initialized to false. And then the distance array is initialized to the cost of the edge from vertex, the start vertex, to any vertex I. I'm sorry, I told you V is the set of vertices. It's not set of vertices. V is the start vertex. Sorry, it's the start vertex. So the distance array is initialized to the cost of the edge from start vertex V to all the other vertices. So this is the initialization part. Then once we start, the vertex V in array S is assigned true, and the distance of vertex, the start vertex, is 0. That's how we start. Then from the next vertex to n minus 1 vertices, we have to perform computing the distance or updating the distance each time. So that is why we use another for loop which starts from 2 to n minus 1. Now we will choose U, a vertex U, from among those vertices not in S, remember, such that we have the minimum distance. That is what I told you. We selected 10, which was for distance of vertex 4 in our example. Why we selected 10? Because that was the minimum distance. And among the vertices which was not in S, then we will make this as true, this vertex U as true, and for each vertex W adjacent to this U vertex U, and the W vertex W is false in array S, we will perform the relaxation technique. So this algorithm, if you look at it, it may seem to be tough, but it is very easy to remember. The first part is the initialization part for 1 to n, for loop for 1 to n. We initialize two things, array S and distance array. Then we make vertex V in array S as true and distance V in vertex the distance array, distance of vertex V as 0. Then from the next vertex, we don't consider start vertex, from the next vertex to n minus 1 vertices, we will choose a vertex U which has minimum distance and which is not true in S, and make that as true. And for that vertex, for every edge or every vertex W adjacent to U, and if it is not false, we perform the relaxation technique. That is, if distance of W is greater than distance U plus cost of U to W, then updated, that is distance of W will become equal to distance of U plus cost of U comma W. And this is the Dijkstras algorithm, or it is also called as shortest path algorithm. Now let us find the complexity of this algorithm. This first for loop is going to run or take run for n times, so it's going to take O of n. Then this for is going to run for n times, so it's going to take O of n. And the statements within this for loop, that is, there is another, choosing the vertex in S and for loop, this for loop is also going to take O of n. So actually, performing the relaxation technique takes O of n square because we have for loop within a for loop. So we can say that the overall time complexity of this algorithm or Dijkstras algorithm is O of n square, which is quadratic. So this is what is all about the Dijkstras algorithm, which uses greedy approach to solve the single source shortest path problem. And this was the last problem in our greedy approach.